Hey everybody! So today we did our Alka-Seltzer lab. Today at midnight, your heat, temperature, and conduction lab is due. So make sure we get that put in. If you're having trouble with that, don't forget I don't think I did put a video up for that one, but let me know if you're having trouble with it. That one was pretty straightforward.
Junior high staff, please check your phones to see if you
So I'm going to go here to Teams. I'm going to go ahead and open up this document here where you can edit it and turn this in, which most of you have been doing a pretty good job with. So in this lab, we will be working with a partner. What factors affect the rate of a chemical reaction when an Alka-Seltzer tablet is put into the water? There is a reaction. So we're still looking into heat here. What is heat? What's temperature? The reaction, however, is not between the chemicals in the Alka-Seltzer and the water. The reactants are actually both found in the solid tablet. The water assists in loosening the reactants so that they can move around and collide and form the products. One of the products is a gas, which we hear fizzling when the tablets are put into the water. The ingredients, the reactants of the reactions are citric acid and the sodium bicarbonate. These compounds are unable to react when in the solid state. When the tablet isn't placed in water, the compounds ionize, allowing them to react. So it shows right here the chemical equation that you won't need until you get into high school chemistry. But here's the two. Here's the two things that we're going to look at today. So the first one, with the Alka-Seltzer tablet, we're going to look at how does temperature affect the rate of reaction, and then how does the surface area affect the rate of a reaction. Okay, so they use the term dissolving in this lab, but this Alka-Seltzer tablet, so this is just a regular tablet, Alka-Seltzer tablet, and this is the guy that you drop it into a glass of water and it starts to fizzle, and you drink it, and it's supposed to help you with a headache, for sinus congestion, and if you have a flu or some kind of fever. Okay? So as you go and do this, make sure you state your hypothesis. So you should have two hypotheses, right? One for the temperature and one for the surface area, because we have two different experiments we're going to run here. Perform the experiment, collect the data. After performing the lab, draw the conclusion. All right, so let's get to it. So the hypothesis: how will temperature affect the rate of a chemical reaction? So this is your if and then statement. So if I put my Alka-Seltzer in a hotter liquid, then it will dissolve faster or slower. If I put it in a cold glass of water, will it dissolve or react quicker or slower? Okay, that's what the hypothesis should roundabout be, right? And you should be able to give me some kind of an explanation, right? We've talked about what do water particles do when they're excited or when they're hot versus what do they do when they're cold, right? We've done like the very first lab we did of the year with the water dye and how the water mixes faster with the hot water, right? So place an Alka-Seltzer tablet on a piece of paper like I have right here. So I'll go ahead and open this window here a little bit better for you here. So I have my Alka-Seltzer tablet here, and it says put it on a piece of towel and break the tablet into two with a spatula. Well, I'm just going to use a razor blade, and I'm going to do the best I can to break it in half. Okay, so I got it in half here. However, I know that I don't have it perfectly in half, so I'm going to try to get both of these sides as evenly matched as possible as far as mass goes. So I'm going to go ahead and turn on my scale here. I believe you guys can see that. Okay. And so anytime I use a scale, remember, I'm going to put my tissue on here, and it reads that mass of the tissue. So the first thing I need to do is go ahead and zero that out. So now it forgets about my tissue here. So I'm going to put my big piece on here. It weighs about 1.98. And the small guy weighs 1.24. So what I need to do is I need to take just a little bit off of this bigger guy to try and even it out a little bit. Okay, so now that weighs 1.51. So I'm going to take these guys out of here. That's 1.51. And this is 1.69. And I'm okay with, Maybe just a little bit more. We might be splitting hairs here. Okay. Whoop. Almost weighed that other tissue piece. All right, 1.60 for this guy. And this guy weighs 1.56. All right, perfect. So these guys are very close. I'm good with that. So next what we're going to do is we're going to have hot water and we're going to have cold water. And I'm going to drop them in there simultaneously. So here's my 1.56. So you're going to want to fill that in the data table below in your data table. Okay? And so first I should say, it says right here, what's the independent variable? What's the dependent? So independent variable is anything that the scientist manipulates. So what did we manipulate in this experiment? We manipulated the water temperature. So I have room temperature water right here. Okay, my room temperature water is 22.2 degrees Celsius. Okay, so that's and then I have my hot water right here, and I'll go ahead and put it in here. It's going to start jumping up for us. And we'll wait till it stops. All right, so it looks like 50 degrees, 50.1 degrees Celsius. Let's go with that. So 50.1 degrees Celsius for our hot water. And so what do we need to do? Well, we need to make sure that they're both at the same, they have the same amount of water, right? Because that could throw off the results. So I'll go ahead and measure 50 milliliters of this hot water out. Okay, there's 50 mils. This is my hot water. And here's my cold water, 50 mils. All right, and I'm going to put these guys in at the same time. So here's my cold water, here's my hot water. So I will put, and make sure you have these lined up on your data table. Okay, so I'm going to put this 1.56 into here, and I'm going to put this 1.6 into my room temperature water. Okay, and if I had a partner here, they would do this clock for me, but I don't, so I'm going to have to do it as fast as I can by myself. So I'm going to drop them in, and then I'll start the timer as fast as possible. So 3, 2, 1. All right, so I don't know if you can hear them going off, but my timer's going right here. And so really, I'm just kind of looking which one is the most vigorous, and definitely the hot water one is going, and it's gone. And that took 23.2 seconds for the hot water. And you can definitely hear this. I don't know if you can hear that fizzling still going on here. So this room temperature water is still going. We'll let it fizzle out here. Still fizzling. I see some solid chunks at the top here still breaking apart. It's starting to slow down. And okay. And I would say that's good right there. So that was our room temperature water. So our hot water, and you need to record this on your data table. So our hot water took 23 seconds to fully react, where our room temperature water then took 52.47 seconds to react. Okay, so you need to make sure you write that down. All right, so then the next thing you need to do, sorry, I can't remember if I did our independent variable. Our independent variable, what did we set? That was our temperature. Sorry, I did say that. But then our dependent variable. So what were we testing there? What depended upon the temperature? Well, it was the rate of reaction, right? We saw the reaction time differ, right? We saw our hot water dissolve much more quickly, twice as quickly, matter of fact, as the room temperature water, okay? So go ahead and you'll fill this table in with all of that previous knowledge that I gave you. Conclusion, was your hypothesis correct? How do you know? Actually, I need to get through these documents a little better. Is our hypothesis supported or is it rejected? Okay, it's not that if it's right or wrong, if it's correct or incorrect. It was just do we have the evidence to support it or not? And so if you said that if you had a supported hypothesis, meaning in this instance you said the hot water will cause the Alka-Seltzer to react more quickly and dissolve, then you'd say my hypothesis was supported and why. And so I want you to actually talk about the numbers that you put in here. Say, well, my hot water, well, tell me how hot was your water. My cold water, tell me how cold the water was. How fast did it dissolve? Use those real numbers that you put up here to use as evidence. Don't just say my evidence supports it. Give me the evidence. I don't want to hear just regular evidence supports it. Don't worry about this one. If you had more time, what additional procedures would you follow? I'm not worried about that one. Go ahead and explain why the temperature then affects the rate of the chemical reaction. Remember, think back to that first lab about the color dye, and we put in the different things of water. All right, so now we're on to our second one. So if you need to go ahead and pause this video so you can catch up and finish up those questions for that first, go ahead and do that. But we're going to go ahead and move on to part two. So now we're going to look at how surface area affects us. So what is surface area? Surface area is length times width, right? So if I have the surface area of this napkin here, I can make the surface area smaller, right? I can fold it over again, I can fold it over again, and I can fold it over again, okay? And so now I have a smaller surface area than I started out with, right? I have my length and I have my width, which is maybe about 1 inch by 1 inch, right? And so this is kind of like our solid tablet here. So we're going to have a solid tablet here, and we're going to have a crushed up solid tablet. Here's our solid tablet with a small surface area, this 1 by 1. But then if I crush it or if I unfold this, then the powder or whatever else is inside begins to come out and is exposed to the area. And as I unfold this, the surface area expands. So now we went from a 1 by 1 tablet, so to speak, to what, a 7 by 7 centimeter tablet or something along those lines. Okay, so now I'm going to go ahead and start this next one. So it says, again, it's the same exact process, except instead of testing, does temperature affect reaction time? Now we're seeing if surface area. So will one chunk, a solid chunk of Alka-Seltzer have a different reaction time than a crushed up one? Okay, and so you need to make a hypothesis about that right now. So I'm going to go ahead and get this guy cut up. Get my scale going on back here. Turn it on. Cut this guy in half. All right. So I have a nice big chunk here. So I'm going to go ahead and measure this guy first. So this looks pretty good. My other one over here split off into 2 pieces. So that's the one I'm going to crush up because I want this in a nice solid chunk because it has the least amount of surface area. But now that this is all broken up, the surface area, right, the amount that's going to be exposed to the water has increased. Go ahead and weigh that guy. And now my piece actually broke. So it's 1.6. Oh, man, we're going to be close. There's my 1.6. And so now what I'm going to do is I'm going to get this as close as I can to 1.6. Okay. So what am I going to do? There's this thing that we got here called a porter pestle. And so I'll put it in here and I'll start to grind it up and make it into a powder here. And we'll throw it on the tissue and go ahead and weigh it. Okay, so I'm going to go ahead, make sure I zero this guy out here. Zeroed out. All right, I'm going to crush this up. I don't have to just sit in here and say all day. It doesn't take long at all to crush this stuff up. All right. Oh boy, guys, I am good. 1.6 on the dot. Are you kidding me? That does not happen in science. Okay, so perfect. We got 1.6 for my solid piece. We got 1.6 for my powder. And you see how this is powdered. So obviously the inside, like I said, we can turn it out and more of it will be exposed to the water more readily. Okay, so kind of think about that if you're still thinking about how to do your hypothesis. So what I need to do is I actually need to get a fresh batch of water here, and they're going to both be the same temperature. So what I'm going to do is I'm just going to get some regular water here, and I've already measured out, pre-measured 50 milliliters, so I'm okay. And so again, these two cups right here, they are the same temperature. But the problem is, again, is I'm going to have some problems putting them in at the same time, especially when this is powder and I have to make sure I get it all in there. So I'm going to do one at a time. Okay, so I'll do the powder first. And you can fast forward if you want, just to kind of, you don't have to wait so long. So I'm going to go ahead, reset this, and all right, and it started. Make sure I get all of that in there. So again, I can hear this fizzling. It's going pretty rigorously. I don't know if you guys can see in there. All right, so we see those bubbles and everything. Definitely starting to slow down now. It's still going. Still kind of going. And I'm going to stop it right there. All right, so that was 32 seconds. So that was for the ground up, or that was the high surface area. So that was 32 seconds. Okay. And next, I'm going to go ahead and do my solid one. So I'm going to go ahead and start my clock over again. Reset. I'm going to put this guy in here. 3, 2, 1. I'm waiting for this guy to go. You can see my phone's getting some moisture on it and stuff. It's definitely still going strong. 24 or 25 seconds in. Definitely can still hear that fizzling going on. Still going on. I definitely see some solid pieces in there still floating around at the top, so they're not, the reactant's not all gone. Seeing there a little better. Getting some bubbles. That's slowing down. Got a little guy on the side. And that pretty well looks done there, guys. Okay. So there for our low surface area, or our big chunk, right? That was our big chunk. That was 101.21 seconds. Or 1 minute, 1 second, 0.21. Okay. 1 minute and 1 second. Okay. So then you guys collected all of your data so far. What's the independent variable here? What's the one thing we changed? We manipulated on purpose as a scientist, right? That's this. That was surface area. We made one with high surface area, which was the ground, and we made one with low surface area, and that was the chunky one. Dependent variable, so what was changed based on the surface area? Well, that was our reaction time again. Okay, so you should have the total, which was 1.6. Total volume was, again, 50 milliliters. And time dissolving, which I showed you guys just earlier, just a second ago. Again, what was your conclusion? What was your hypothesis? Go back to your hypothesis. Was it supported? Was it rejected? And then tell me why, right? Don't just say my evidence supported it. Show me. Bring your numbers down here and talk about your numbers. Discuss them, why they supported it, why they rejected it. Okay, and if you got it wrong, if your hypothesis was rejected, that's totally fine. Okay, just make sure that you're telling me why, and you're using real numbers and stuff down here in the conclusion. Again, this one right here, you don't have to do for this one. Explain why the surface area affects the rate of the chemical reaction. Okay, so think about the water particles and what happens. Go back to that first page and how it talks about how the chemical reaction occurs with the collisions and stuff like that. All right, but I think that's it for this lab. You guys can pause this video, go back and do whatever you want with it. But again, get a hold of me if you guys need any help. Bye.